we are discussing the algebraic structures, and we have defined the algebraic systems as a set of finite set of elements which is non-empty, and some binary operations or some n-ary operations in general that operates on this set. We have also read some general properties of algebraic systems, and mainly now what we are doing, that we are trying to identify or to form the to define the different algebraic systems depending on the properties that they satisfy. We have already read the semi groups and monoids, the simplest algebraic systems. Now, today we will read the group, which is the most important algebraic systems, or we can tell the algebra, and which have a number of application areas in almost all the streams of engineering, mathematics, in computer science. So, we will read the group today as an algebraic system. Now, if we remember, we have read the general properties of algebraic systems as the closure property, the associative property, the commutative property, the identity, and the inverse. Now, the semi group and the monoid that we have defined, that mainly they follow the or they satisfy the property of closures, then associative, and if the identity element it has, then it is a monoid, otherwise it is a semi group. Now, group is a we can define that again this is a algebraic system which actually satisfies the all three properties that the monoid satisfies, that means the closure, associativity and the identity element it has. Now, in addition, if it has the inverse element, then we will be telling this as a group. So, we define or we write in that a group G, we give the notation like that as if G is the set of elements and dot is the operation. So, is a set of elements with binary operation dot that associates to each ordered pair AB of the set G of a element A dot B, where dot is the operation that we have defined. So, A dot B, and that is also in G, such that the following properties must be hold. Now, the properties are one, that the closure that means if A B belongs to G, then A dot B belongs to G. Then associative, that means if A B C belongs to G, then A dot B dot C is same as that A dot B dot C. 3 is our identity element. That means there is an element E exists, and elements E belongs to G, then for all A belongs to G, A dot E equal to E dot A is A only. Now, up to these 3 properties we have seen, and that then if it holds, then we call this is monoid. Now, in addition, if the system has some inverse element, inverse element exists, that means for all A belongs to G, if there is an element A dash belongs to G such that A dot A dash equal to the A dash dot A is the identity element only. Now, see, we have only these properties we have added. This is my added property with monoid added over monoid, and we tell that then this forms a group. Okay. Now, if the group satisfies the commutative property also, then it is called a abelian group or the commutative group, as we have defined for monoid and the semi group. So, if it also satisfies the property of commutativity, that means that is the property, I write that 5 that B dot A equal to A dot B. For A B, belongs to G. Then it is a called an abelian group. Or we can tell this is a commutative group. Now, we see one simple example, that if my set is we see if the set is a real number, normally we denote that is a R, and the operation is multiplication. Then it is closed. The closed, since if I take two real number and if we multiply, that is also an element of the set R. It is associative with real numbers. The associative property also holds, because its final result is an real number, that is also an element of R. So, this is associative. Then the identity element exists, and we know the multiplicative identity is 1. Multiplicative identity is 1, and now the inverse also exists. Since it is a real number, so the inverse also exists. So, it forms a group. So, R with multiplication forms an algebraic system, it is a group. Now, if instead of this R, the real number, if we consider the set, now if the set is integers, again positive, negative with 0, and the operation is multiplication, then it is closed. Associative, identity exists, that is equal to 1, multiplicative identity 1, but there is no inverse exist, since it is the set of integers. So, no inverse exist. So, it is not a group. So, integers, so it is not a group. Integers with multiplication as the operation, it is not a group. Now, there are some other simple definition of groups we always we read. One is called the finite group, finite and infinite group. If the set is finite, then it is a finite group, and then the size of the group, and in this case if it is a finite group, the size of the group is called the order of the group. Is called the order of the group. Now, if the set is infinite, then it is a infinite group. So, simply infinite or finite, it actually depends on whether the set is finite or infinite. So, if the set is infinite, that means the set has infinite number of elements. Now, if we consider a set A, say we consider some properties of group we now study. We consider a set A equal to say n number of elements it has, and the say we say dot is a binary operation, and A dot, that means a set with the binary operation dot forms a group. Now, the effect of this operation dot on the elements of or the n number of elements of A, that we can represent by a matrix. On the elements of A, or I can write on the n elements of, because n element set. So, n elements of A can be represented as a n by n matrix. And we will see some properties. If it is a group, then from directly from the matrix, how we can identify some of the properties, group properties. So, I can write in this way, the matrix will be like, I can give A1, A2, A3 up to An. The operation we give here, and then again A1, A2, A3 and then An, and this is a we see this is a n by n matrix. If we represent the elements that A1 dot A1, that the after operation, if we represent this as a C11, C12, C13, C1n, similarly 21, then I can write that Cij is Ai dot Aj. That means, if I consider some Cij here, some Cij. So, here I will be getting that Ai elements, Ai is here and as if some Aj. So, Cij is Ai dot Aj. Now, we identify some properties that each element here, since it is a group. So, each element has an inverse. Okay. So, now we give a property of a group, that give a property that no two elements in a row or in a column is same. Now, how we can show that thing? See, if I have two elements, say assume the two elements are same. So, let two elements C I j and C I k are equal or same in a row. We consider that in a row two elements are same. Now, what is C I j? Now, C I j is A I dot A j and C I k is A I dot A k. Now, if we assume that C I j and C I k are same, then now if C I j equals C I k, that means A I dot A k, sorry, A I dot A j is A I dot A k. Now, since it is a group, so there exists one inverse element, and let this inverse element is for A I is A I inverse. So, I write, since it is a group, so there exists an inverse element of A I of A I. So, I can write A I inverse dot A I dot A j is, in both side we do the operation. dot. Then A I inverse A I is the identity element. So, E dot A j is E dot A k. Since this E is same element, E dot A j is E dot A k. We know E dot A j is A j only, and E dot A k is A k only, because that is my E is my identity element. E is identity element. So, then A j equal to A k. Now, since it is a set, so no two elements, these A j and A k are same. So, since no two elements of the set A is same, that means A I A j not equal to A k. So, C I j not equal to C I k. So, no, and similarly we can prove that for columns also no two elements in a column are same. So, similarly we can prove for columns also. Now, as we have defined the cyclic monoid, here also we can define the cyclic group. The definition is same, the group is cyclic is a power of an element, say A belongs to G, and here A is called the, and say the power is like, the power is A to the power k, where k is some integer, positive integer. And A is called the generator. Now, a property of a cyclic group is, already we have this thing we have seen for monoid, and here also it is same, that a cyclic group is always commutative in nature. And maybe finite or infinite. So, we have read some the definition of group, some properties of group, and in the we will be continuing the group properties and some examples in our next lecture.